All right, so 3.6 is a nice way to sort of round out a lot of the sections that came before this. All right, so we can think about 3.6 as really being like a culmination of 3.1 all the way to 3.5. Okay. I think that one sort of suggestion I have in terms of studying, sort of thinking about how we put together a whole story, is that sometimes when we study backwards in a unit, so for example, maybe starting with 3.6 as we prepare for that next exam, starting with 3.6 could actually be a really good way to make sure that you're getting the important concepts of 3.1 through 3.5. And I know sometimes we think about studying backwards as like, maybe that's like a weird thing. We've never done that before. But I would encourage you to give it a try and see how it feels to review the content from the other end and kind of think about how all the little pieces we learned along the way actually fit into that big story. Okay. So let's take a look at this polynomial. All right. So we're given this polynomial f of x equals x cubed minus 6x squared minus x plus 30. And what I'd like us to do is try and answer these first three questions, okay? So determine the degree and the leading coefficient of the polynomial, determine the end behavior of the polynomial, and then determine the y-intercept, all right? So let's go ahead and start with determining the degree and leading coefficient of the polynomial, all right? So what degree would we say that this polynomial is, and how do we know? All right, I like that, Ellie. Well, we got a third degree. It's degree 3. And how do we know that? Like, how come it's not 3 plus 2 plus 1, right? Because sometimes we do that. It is the highest degree. So in particular, in standard form, we choose the highest degree. Okay. The key here being in standard form. Standard form means it's already multiplied out. Okay. What is the leading coefficient? It is a 1. Good. And in particular, I'm actually going to put a negative 1. Okay. All right, so we got degree 3. It's in standard form, so we just choose the highest degree, and we know that leading coefficient is positive 1. Okay. These you can find if you need a little review. This would be a good place to go back and take a look at section 3.3. Okay. All right. Part B, determine the end behavior of the polynomial. Someone tell me which two options we have for end behavior. Okay, so we could have down, up, or up, down, right? So those are our two options. And maybe we make a note for ourselves that these options are because the degree is odd, right? And can someone remind me which section that comes from? Like if someone wants to go back and review the end behavior, what section would they find it in? All right, can we have a tiebreaker? Is it going to be 3.3 or 3.4? All right, so let's go and we'll jot down a 3.3 here. So in case we want to go back and review how we know this, we would go back to section 3.3. Now of these two though, which one is it going to be and how do we know? All right, I agree, it's going to be down up. And just to make that thinking clear, how do we know that it's going to be down up? Leading coefficient is positive, right? So sometimes we know that leading coefficient is 1, but then it's like an extra step for us to think, oh, is it +1 or -1? But if we write that positive, it might help us make a decision later on down the road, right? And so that's sometimes a skill that I find helpful is when I write more than I need to, I actually am helping myself think about what I'm actually trying to answer. Okay. Good. All right. So last question here, determine the y-intercept. What section would someone go back to if they wanted to take a look at how they find a y-intercept? All right, so maybe we'll jot that down, taking a look at 3.3 to find that y-intercept. And can someone tell me what the process of finding a y-intercept is in general? Right, let's talk about the process, but make sure we also know why we do that process the way we do. All right, I really like the way that Dallas framed this. To determine the y-intercept, 0, comma, a number. If we have 0, comma, a number, what does that mean that x equals? Yeah, x equals 0. And so this is all we're going to do. We're going to take our function, we're going to plug in 0 for x. But the reason we do that is because every y-intercept has an x value of 0. Right? So f of 0 equals 0 cubed minus 6 times 0 squared minus 0 plus 30. And we end up with 30, right? But if all we write is 30, that doesn't answer the question. We want to make sure we write it as the intercept it is. So we would want to write our final answer as 0, comma, 30. Okay. All right. So hopefully this was a good review of some of the more important concepts and processes from 3.3. And if you haven't had a chance to look over that yet, I would encourage you to do so before you turn in the quiz this evening. I think that will be helpful. Okay. All right. So let's take a look at this. All right. This is a continuation of the same problem. So to find the x-intercepts, here's what we are going to do. All right. We're going to go through first and we're going to list out all possible rational zeros, okay? And here's what I mean by that. We're gonna make a fraction, all right? And we're gonna do factors of the constant term. And we're gonna divide it by factors of the leading coefficient. And then we're going to make sure we consider positive and negative versions. Now this requires us to go back to our equation. And the factors of the constant, what's the constant in my polynomial right now? It's 30, right? So that number on the end is where we're going to get the factors of 30 are going to go on the top. And factors of the leading coefficient, where do we find that leading coefficient? Right at the front, and that is +1. Okay. So let's list out these factors. What do we know to be factors of 1? Well, that's just 1, right? The leading coefficient is just 1, so those factors are just 1. And then to find factors of the constant, well, factors of 30, I could do 1 and 30. What else are factors of 30? Yeah, 3 and what? 3 and 10, good, 2 and 15. And I think there's one more pair out there. Yeah, we got it, 5 and 6, okay? So we took all the factors of the constant, we put them over the factors of the leading coefficient. Now, the really cool thing about what we've just done is sometimes we want to guess where our graph, like if we didn't know what it looked like, where that graph would cross the x-axis. It turns out that what we've created right here, what we've created right here is a list of possible x-intercepts. Okay. So instead of saying, oh my gosh, the x-intercepts could be any single number in the entire world, that feels very overwhelming, right? Instead of saying that, we're saying, here's a list of some possible x-intercepts. And if we choose from this list and we compare it to our graph, that might actually be helpful in figuring out what we need to divide by, all right, to find out the factorization, all right? Now, if I sort of scroll a little bit to the end, let's look at this last step so we kind of know where we're headed. The last step says, write the linear factorization of the polynomial. That means I want to write f of x equals a bunch of linear terms multiplied together, however many there are. I want to be able to write that list. So in order to get there, all of these steps in between are meant to help us get there, figure out what those factors are. Okay. So let's take a look at this list right here. Of the items in this list of possible x-intercepts, do you see any that are on this graph as well? Two, 5, and 3. Okay. So if we kind of look at this, we've got it crosses at maybe a -2, +5, a +3. Okay. So what does that tell us? That tells us that maybe x equals -2 is a 0. That maybe x equals 3 is a 0, and that x equals 5 is a 0. If x equals 5, what factor did you set equal to 0 to get x equals 5? Nice. Okay. If that's true, and x equals 3 is a 0, what factor did that come from? All right. And this last one, if x equals -2 is a factor, or is a 0, what factor did that come from? Nice. Okay. So according to my graph, a good guess for the linear factorization might be x times 2 times x minus 3 times x minus 5. So I'm going to go ahead and write that down below as a guess, okay? I think this could be x plus 2, x minus 3, x minus 5. Okay. And where did we get that? This is our guess from the graph. All right, so we've got a guess about what it should be, but let's think about this as a process, because sometimes these numbers aren't going to be nice numbers and it might be a little harder to guess. Sometimes we might not have a graph, right? And so we want to think about how we can make sure that this is a good guess. So let's take a look at part E. Part E says use the graph to identify 1, 0 and its corresponding factor, all right? So if we were to choose our favorite one out of here, it doesn't really matter. Maybe let's choose x equals -2, okay? And so I'm going to use this graph and I'm going to say that x equals -2 is a 0. So x plus 2 is a factor. All right, so x minus 2 is a 0, so x plus 2 is a factor. Now you could have also said x equals 3 is a 0, so x minus 3 is a factor. Or you could say x equals 5 is a 0, so x minus 5 is a factor. Any one of those would be okay. All right, part F. Use long or synthetic division to confirm that the 0 from part E is a 0. So if I wanted to use division, all right, let's kind of choose right now as a class. Would we like to do long division or synthetic division? All right, synthetic to practice. I love it. So we're going to draw that half square. And we're going to think about what number goes in this half square over here. And we want to think about the coefficients that we would have to put over here. Right? So number that goes inside the half square is going to be your 0. So I'm going to go ahead and put a -2 right in there. And then to get the coefficients for my yellow part, I need to go back to my original function. And so based off of the f of x given, I want to choose these coefficients. So I'm going to do 1, -6, -1, and +30. Okay. 1, -6, -1, and 30. Skip a line, draw a line. All right, first things first, we're going to bring that 1 right down. 1. We're going to multiply. -1 or -2 times 1 is -2. I'm going to go ahead and add. -6 plus -2 is -8. -2 times -8 is going to give me 16. -1 plus 16 is going to give me 15. -2 times 15 gives me -30. 30 plus -30 gives me 0. 0 is my remainder. That means that x plus 2 is a factor. This also means that we can write our f of x as x plus 2 times, what's the other factor?
X squared minus 8x plus 15.
Good. We're grabbing that quotient line, right? That goes right there. We have our linear factor. And so we are starting to factor this thing, right? We started with like an x cubed, and now we're able to get it into a linear factor and a quadratic factor, okay? Now remember, our end goal is to write a linear factorization. This part is already linear. The only part I need to continue to factor is the green part. Okay. Now, for some of us who are feeling very confident in our factoring, I bet we could factor x squared minus 8x plus 15, right? But for the purpose of this problem, I want us to go through this idea again. Let's use the graph to find a 0, write the factor, and practice that synthetic division, okay? So for the next part, part G, let's use x equals 3 as a 0. All right, so x equals 3 is a 0. So what's the factor that goes with that? Good, so x minus 3 is a factor. Well, if x minus 3 is the factor and x is equal to 3 is a 0, that means that my little inside this half square part should be a 3. Here's what we're going to do, okay? Remember, this part, x plus 2, is already factored. We only want to think about how to factor this green part. So instead of using these coefficients again, I'm going to use the green coefficients. So 1, -8, and 15. 1, -8, 15. Right. What do I hope to get down here if I want that x minus 3 as a factor? Yeah, I want to get a 0 there, right? So let's see if we get a 0. We're going to drop that 1 down. 3 times 1 is 3. -8 plus 3 is -5. 3 times -5 is -15. Ooh, yep, I got a 0. this 0 means that x minus 5 is what that part becomes. And then this part was our x minus 3. This means that x squared minus 8x plus 15 is equal to x minus 3 times x minus 5. And so if we put this all together, let's see what we found so far. We found x plus 2 as a factor. And then the green part, we broke it down into x minus 3 times x minus 5. That means all together we have x plus 2 times x minus 3 times x minus 5. And look at our initial guess from the graph. X plus 2 times x minus 3 times x minus 5. I want to make a couple notes here for us. All right. Sometimes we will have imaginary factors here. Sometimes we will have imaginary factors here. Okay. Other times, we may need to use the quadratic formula. Okay. But we don't want the quadratic formula to be our go-to. We really want to embrace this idea of factoring and thinking about how we can use that. Okay. Now I sort of skipped a step here. It says write the polynomial in linear and irreducible or reducible quadratic factors. All that means is the first 0 we put in, that x plus 2, and then our factor x squared minus 8x plus 15. This would be our reducible quadratic factor. Reducible because we were able to turn it into 2 linear factors. Okay. And these linear factors had real numbers. But you might be wondering, well, how are we going to know if we have imaginary factors? It turns out that these imaginary factors come from what we're going to call irreducible quadratic factors. So knowing whether something is reducible or irreducible is actually going to be really important. Okay. Let me pause here for a moment and just kind of see if there are any questions coming up for folks.
I had a question on when you were going over D, list all the possible rational zeros. In order to narrow down that list, is it possible to kind of like look at the least common multiples? Or every time you kind of like go through and test these, you want to do all possible?
You want to do all possible.
Okay.
Yeah. And keep in mind that we're really utilizing our technology here, right? So we're just writing a list, but then we're cross-referencing it with a graph and thinking, okay, of this list, which one are actually possible ones? So it doesn't mean that we have to test every single one of those. We want to make sure that the technology is helping us minimize our trial and error, so to speak.
Okay.
All right. So that's sort of a big problem in the sense that we started with some things that we know, and then we layered on a bunch of new things. And so on this next page, you'll find some theorems. And some of these theorems we've actually already used, and now we're just giving them names, okay? In particular, we have something called a factor theorem, right? The factor theorem. And so we have that k is a zero of a polynomial if and only if x minus k is a factor of that polynomial. That is what we were using when we said like negative x equals negative 2 is a 0. Then we said x minus negative 2 is a factor. That's where that plus sign came from, right? X minus negative 2. But then we also said if x equals 3 is a 0, that means that x minus 3 is a factor. Right? That's all the factor theorem is, right? It just tells us what, if we know a 0, what is the factor that goes with it. And that's helpful when we want to write out that linear factorization. Okay. There's a second theorem that we used here. I sort of snuck in there. And that is called the rational zero theorem. Okay. The rational zero theorem. The rational zero theorem is what we did when we said, let's list out the possible factors. All right. This is a very fancy way of saying it. The same thing we had before. That list of P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. Right? That is the same thing as saying that plus minus factors of the constant over factors of the leading coefficient. Right? And I wanted to include the textbook, fancy language, symbols, because I think it's important for us to realize if we understand this, we can also understand this, right? That's like a confidence thing. Like, do we feel like we are good enough to even understand what that means? And the answer, folks, is yes, you are, right? But we just need to think about maybe some other ways to express it so that it makes more sense to us, right? And again, this rational zero theorem just tells you like it's like a narrowing down list. Instead of choosing from all of the possible numbers, we're only choosing to look at the ones that are factors of the constant over factors of the leading coefficient. Okay. The last thing I wanted to share with you from your textbook, okay, so again, this is from your textbook that OpenStax, it is free. You can go back to this textbook anytime you want to in future classes. If you're like, oh, I forgot about that thing, there's a free online textbook you can look back at, right? And so this how-to just tells you how to find that list, right? How do we find the factors of the constant? How do we find the factors of the leading coefficient? And then just making sure that we have the positive and negative candidates. I am going to ask us to cross out this last line here because we are going to compare with a graph. Okay. I'm going to compare this with a graph. All right, so let's spend some time going back into practice, all right? Because I think the more we kind of go through this process, the more we can start to think about a lot of these things that I'm saying, like, oh, this is important because of this, or this process actually means we're finding this, okay? So let's take a look at this practice question right here. And let's take a moment to answer questions A, B, and C. All right. All right, so let's start off with the degree here. What degree is this polynomial? It is degree 3, and that leading coefficient? All right, that's a positive 3. All right, great. What about the end behavior? What are our two choices here? Yeah, down, up, or up, down. And which one of these is it? And how do we know?
Down, up, because the leading coefficient is positive.
Good, down, up, because that is positive. Perfect. All right. Last of the 3 refresher questions when we're determining the Y-intercept. All we're doing is plugging in 0 for x. So we'll get 3 times 0 cubed plus 9 times 0 squared plus 0 plus 3, which equals 3. But we're going to want to write a coefficient, or we want to write a coordinate. We don't want to just leave our answer as 3. We'll say 0, 3. And again, all 3 of these you can find in section 3.3 of your textbook. Right? Now let's go ahead and copy this. Oh. Okay, that's fine. We'll just write it again. All right, so if we are looking to apply that rational root theorem or rational zero theorem, we want to list all the possible rational zeros, right? So we're going to go ahead and start with our plus minus, draw that fraction line. What are the factors of the constant? Excuse me. Yep. 1 and 3. Good. And what about the factors of the leading coefficient? Same, right? Because our leading coefficient happens to be the same number, right? Now, if I wanted to write out all of the possible rational zeros, I might say I have plus or minus 3 because 3 divided by 1 gives me 3. I might also say plus or minus 1 because 3 divided by 3 is 1, but also because 1 divided by 1 is 1. But what's the last possible zero that we could have here? Good. 1/3. And that's just because we have a 1 divided by a 3. So that's the third possibility. So instead of writing out like a whole long list like this, we sort of clump it as the factors, and then we're able to compare it to the graph to see what we actually need. Okay. All right. So now let's compare it to our graph. According to the graph, what would be our best guess to pick from our list? -3. Good. Because right here we have x equals -3. Let's think ahead. Let's think about that factor theorem. If x equals -3 is a 0, what is the factor that goes with it? Good. X minus -3, or we might just say x plus 3. Okay. Now, let's look at this graph for a moment. How many times does this graph cross the x-axis that you can see with your own eyeballs? 1, right? It only crosses 1 time. Here's what this means. This means that there's only one real zero. Okay, there's only one real zero. How many could we have at most for a cubic? And this goes back to a different section, right? How many? What's our maximum number of zeros? It's 3. Well, here's the thing. There are 3 zeros on this graph. You can only see one of them. If there are 3 altogether and there's only one real one, the other 2 have to be imaginary. Right? Another way to say that is that maximum number of zeros is always achieved. If you have the maximum number of zeros is 3, you're going to have a total of 3, but only some of them might be real. The others will be imaginary. And because they're imaginary, we don't see them on the graph, right? We only see that one of them crosses. So let's kind of work through this process and see if we can't figure out what that imaginary zero is going to be, what they're going to be, what those 2 that we don't see on the graph, what those factors are going to be. Okay. So in part E, it says use the graph to identify 1, 0 and its corresponding factor. We only see 1, so we really only have one thing to write down. X equals -3 is a 0. So X plus 3 is a factor. Okay. X equals -3 is a 0, so X plus 3 is a factor. All right, so if we're going to set up our synthetic division here, what number goes inside that little half square? Yeah, let's get that -3 in there. And what am I going to write for my coefficients over here?
Uh, 3, 9, 1, and 3.
3, 9, 1, 3. Yep, we're just going to grab those coefficients from our f of x, right? 3, 9, 1, 3. All right, let's walk through our synthetic division. Drop the 3. -3 times 3 is -9. -9 plus 9 is 0. -3 times 0 is 0. 1 plus 0 is 1. -3 times 1 is -3. 3 plus -3 is 0. My friends, we have confirmed that x plus 3 is a factor because we ended up with a remainder of 0. Okay. Interpret this for me. 3, 0, 1. What does that mean?
3x to the second power plus 1.
Good. Plus 0x plus 1, right? That's what that 3, 0, 1 really stands for. And so what we're going to do now is we're going to go ahead and write our polynomial in our linear and irreducible quadratic factors. And we'll talk about why those are called irreducible quadratic. Okay. So our f of x is going to equal x plus 3 times 3x squared plus 1. This is my linear factor, and this is my irreducible quadratic factor. All right. What does it mean to be an irreducible quadratic factor? Let's define that. It is a quadratic factor that has imaginary solutions. Okay, so when we say irreducible, we mean that there's no real answer for it, but there are imaginary answers. Okay, there are imaginary answers. So let's think about where these imaginary answers come from. If I have 3x squared plus 1 equals 0, how do I solve for x? All right, let's walk through that process together. How do we solve for x? We're going to subtract 1. I like that. 3x squared equals 1. All right, now what? Divide by 3. Good. So x squared equals, whoops, it's a -1 over there. So x squared equals -1/3. All right. And now what is our last step to get x all by itself? Square root each side. Good. So we get x equals plus or minus the square root of -1/3. right? And this is where we have to draw upon some knowledge from, say, section 3.1, right? How do we rewrite this?
You could you could put the square root on the top and bottom.
Okay, but in particular, what about this negative situation? Yeah, right. So Lisa, we could do 1/3 times -1. Right, so we could do square root of 1 times square root of 3, or divide by square root of 3 times square root of -1. But how do we write the square root of -1? With the I. Good, good, good. So really we have x equals plus or minus 1 over root 3 I. Okay. The square root of -1, we don't write it like that. We write it like I. Okay. So when we solved for the zeros of 3x squared plus 1, we got imaginary things. And in fact, we got a positive imaginary and a negative imaginary. So we got two imaginaries. And if we look back at our graph, remember we said we have one real, and since it never crosses again, we actually have two imaginary. Right? And so that's how come the imaginary ones come from that irreducible quadratic factor. Right? All right, so we now have to write the linear factorization, right? Right now we have part of a linear factorization, but this part is still quadratic. So we get to keep the part that is linear already, and we're only going to work with the part that is the irreducible quadratic part, right? And I'll tell you what, we already did a lot of the work we need to do over here, okay? So in this irreducible quadratic factor, what is the leading coefficient? It's a 3. So I'm going to suggest that we go ahead and pull out that leading coefficient, right? If I factor out a 3, what's left in the rest of it?
X squared plus 1 over 3.
Good. X squared plus 1 over 3. Good, good. All right. Now we have our x plus 3 times 3. And if I factor x squared plus 1/3, I'm going to get x plus 1 over root 3I and x minus 1 over root 3I. Or x plus 1 over root 3I and x minus 1 over root 3I. Let's make a note for ourselves that these two come from our solution over there. This question says, find the linear factorization. Linear, 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 constant. That's okay. That means that our linear factorization, we usually bring the constants to the front. So we'll have 3 times x plus 3 times x plus 1 over root 3I times x minus 1 over root 3I. And this would be our linear factorization. So let me pause here for a moment and let's see if we have any questions so far.
I actually have a question. It's kind of like what I asked on Discord. So technically, like that is like the plus or minus 1 over the square root of 3i. That's like a 0. But whenever you like ask a question, like find the x and y-intercept, that isn't a part of the x-intercepts, right? Or okay.
Yeah. So when we say x-intercepts, we're typically looking for the real ones that we can actually see on the graph. And so that's why we would only choose this one.
Okay.
Okay. All right. So I think what we're going to do now, we're going to do one more example. We're going to skip to the end, and then if we have time, we'll come back and do a second example. All right. So let's take a look at this example number 2 over here. The first 3 questions I think are pretty familiar to us. So let's kind of zip through those, and then we'll spend more of the time working on this factorization and the synthetic division, because that's really the new part for today. Okay. So in a look at this polynomial, we have 2x cubed minus 3x squared minus 4x plus 6. Our degree here, I hope we agree, is 3. And our leading coefficient, I hope we agree, is going to be a positive 2. If we look at the end behavior, as I think it was Avi said so well earlier, that the end behavior is going to be down up because the leading coefficient is positive. Right? So just because we write this down, we also want to make sure we know why it came from that. Right? So that would be something I would maybe want you to explain, like how you got that. And all you would say is because the degree is odd and the leading coefficient is positive, we know that the end behavior has to be down up. And then last but not least, we're going to determine the y-intercept by doing f of 0. We're going to plug 0 into our equation. Being super careful, we know 0 times a number is going to give us 0, so we get an output of 6. But we want to make sure we write the y-intercept as a coordinate, 0, 6. Okay. All right, let's list our possible rational zeros. All right, this part is newer for us. So I'm going to give you a moment to sort of write down what you think the factors are that belong on the top and the factors that you think belong on the bottom. Right, so let's practice the things that are newer for us. And I hope for the denominator, we get like a 1 and a 2, because those are the factors of 2. And on the top, we're going to have like 1 and 6, but also 2 and 3. Okay. Now, if I were to use the graph and give a guess as to what those real roots might be, let's zoom in on this graph right here. what do we think would be one good guess to pick from that list? Like I would say, looking at this graph, maybe 6 is a really bad guess, right? Because we don't even see 6 on the x-axis. So I see maybe a 1/2 is a good guess. So 1/2 would be
-3/2.
here. I'm not sure that we see a 1/2 there. So a -3/2. -3/2 would be like maybe here. It looks kind of close, but I don't know if that's exactly right on -3/2. Okay, maybe what about a +3/2? That'd be somewhere there. Okay, maybe that one's the closest out of the guesses, right? So if we had x equals 3/2, what would be the factor that goes with that?
Uh, 2x minus 3.
Ooh, okay. Tell me how you got that.
Multiply 2 to both sides and then subtract 3 to get like 0 on one side and then just like the factor on the other.
Yeah. So some of us might have said x minus 3/2, right? Because that is literally what the factor theorem tells us. This is just sort of one more step, and it tends to be a common step when we have a fraction here. But also, it tends to be a common step if this leading coefficient, 2, matches that leading coefficient. Okay. So, according to our graph, a good guess might be x equals 3/2 is a 0. So x minus 3/2 or 2x minus 3 is a factor. Now, we're going to hold on to this piece because this, I think, is a little bit less important for step F. We will come back to this in a later step. Okay. As far as step F goes, I just need to put my 0 in that half square. And then I need to write out my coefficients. And if I look back at my polynomial, I believe I had a 2, a -3, a -4, and a +6. All right. And you'll notice that I've been asking us to do a lot of these questions and they have fractions in them and we're trying to multiply fractions. This is intentional. I want to do this because I think it makes us better mathematicians. I think it makes us feel more comfortable to work with fractions, right? Even if it's scary at first, it's like this idea that over the course of the semester, we're building that confidence for working with our fractions, right? So let's go ahead and work through the synthetic division. We're gonna drop the 2. 2 times 3/2 gives me a +3. -3 plus 3 is 0. A 0 times 3/2 is 0. -4 plus 0 is -4. -4 times 3/2 is going to give us -6. And -6 plus 6 gives me 0. Got a remainder of 0, so we are good to go. We do indeed have a factor. We've confirmed a factor, okay? Now, we have at the bottom then 2, 0, and -4. What does that stand for? 2, 0, and negative 4. (2x squared minus 4). Perfect, perfect. This stands for 2x squared minus 4. And if you think back to earlier in section 3.5, I was like, oh, here's our quotient. But then for one problem, I was like, here's our almost quotient. And it was an almost quotient because we had a leading coefficient that wasn't 1, right? Now we have one that's 2. What did we do to get the actual quotient? We have to divide by that leading coefficient. When we divide by that leading coefficient, we're going to get x squared minus 2. So let's pause for a moment, see what we found out so far. We found out that one of the factors of f of x is 2x minus 3. The other factor is x squared minus 2. This is not a linear factorization because I have a linear here, but I have a quadratic here. I put the word irreducible here, and I want us to think about if x squared minus 2 is irreducible or not. In other words, can we solve this to have real solutions? All right, how would we solve this? X squared minus 2. Okay, we'll add 2. X squared equals 2. Square root both sides. All right, so we get x equals plus or minus what? Square root of 2. Is that real or imaginary? Yeah. This is real. Right? This is real. Sometimes we think too fast, our brain gets a little confused and we're like, oh, square root, that's not real. It's not a nice number, but it's still real in the sense that there's no negative underneath that square root. Okay, there's no negative underneath that square root. What that means is when I go to write the linear factorization, I can keep the linear factor I already had. But how can I write x squared minus 2 as a pair of linear factors? We already have sort of the answers somewhere else on the page.
So you would do x minus the square root of 2 and then x plus the square root of 2.
Yeah, these two are our zeros. Okay, so let's write this out in a sentence for a moment. If x equals square root of 2 is a 0, then the factor theorem says then x minus square root of 2 is a factor. I know it has a square root, and that probably looks weird and uncomfortable, but it's still a factor, like it's still okay. All right, we're sort of beyond the stages of our academic careers where if we get like a square root or a fraction, like that's a wrong answer, right? We want to sort of start to remove ourselves from that and embrace the fact that sometimes we leave things as radicals and that's actually considered exact or actually the answer that we're looking for. Okay. Everything here is a linear factor, and so together it makes the linear factorization of our polynomial.
So it's okay to leave the first factor 2x minus 3 in that form, or do you want us to extract the constant like you did above?
Great question. I would say that if this were a 2 and this were a 2, I would go ahead and pull out that constant. But if it's not, like if there's no common factor, I would just leave it. I think in the other example, maybe one thing that was confusing, like why we left why we didn't keep that 3 there, is if we are continuing to factor something, it's probably easier if that coefficient is 1. So like this 3x squared plus 1, we were continuing to factor it, so it would be easier if we have this as a 1 instead of a 3. But if I look down below, I've already, like the thing that I'm factoring, continuing to factor, already has a coefficient of 1. So I wouldn't take anything out of there. If that makes sense. I would encourage you to try it different ways though, but at the end, the one thing you really want to consider is, does your leading coefficient in the linear factorization match your leading coefficient in the original question? Right. All right, based on time, we're going to skip to example 4 right now. Take a look at 4 and 5, just because I know that there are quiz questions like this, and so I want to make sure that we're okay with the process for this. All right. So example 4 or 5, we are given some zeros. Okay, so these right here, 5 and 3 plus 2i, are zeros of a polynomial. And in particular, 5 is a real 0, but 3 plus 2i is an imaginary 0. There's a really important point that I want to make about the imaginary zeros, okay? And that is this: imaginary zeros always come in pairs. There's never just one imaginary. That means where there's one imaginary 0, there must be another. So I see 5. 5 is real, but then I see 3 plus 2i. That's an imaginary one. But if there's one imaginary, there has to be another imaginary. So if 3 plus 2i is a 0, then so is 3 minus 2i. Plus, minus. I talked about something called complex conjugates in the 3.1 lecture video. We're using those complex conjugates here. So if 3 plus 2i is a 0, so is its complex conjugate. It's really important that you do that part first. Then we're going to write out the polynomial, and then we're going to FOIL, multiply all these binomials. Okay. So help me out here. If x equals 5 is a real 0, what factor did it come from? Good. This 5 gave me this factor. If 3 plus 2i is a 0, what is the factor that goes with it?
I'm not super sure, but I got x minus 3 divided by 2, all of that squared plus 1. I haven't done like any simplification yet, but I don't know. I did the 3 plus 2i equals 0 and just tried to move it, or equal to x, and then try to move everything to one side with the x.
Okay, I like that. So let's kind of do that. Let's do that up here. X equals 3 plus 2i. If I want to get it equal to 0, how do I move things to the other side? Like, how do I move the 3?
Minus 3.
So x minus 3 equals 2i. How do I move the 2i?
Divide by 2.
Why are we dividing by 2?
Because 2 is like 2 times I.
It is, but I'm not solving for I. I want to get something equal to 0. Right? Because when you did x equals 5, you did x minus 5 equals 0. Getting the right-hand side equal to 0. How do we follow that same structure here? Yeah, why are we dividing by 2i?
So you just subtract 2i?
Ah, okay, because 2i is just plus 2i, so if I want to move it, I just subtract it. Right? It doesn't matter how weird it looks, we still have to think about our order of operations and how that might, if we're adding something and we want to move it, we got to subtract it. If we're multiplying by something, then we divide it. But whatever that operation is, still that same operation. So right here, this is our factor that goes with it.
So it doesn't matter if we have the I. We don't want to try to get rid of the I.
Yeah. The I is actually going to go away in the end because of that complex conjugate. So we'll have I's for a little bit in our factors, but that's very similar to, where did it go? Like this one, we had our linear factorization. It had I's in it, and that's okay.
Okay.
It's weird, I know. It's okay to be not convinced right now. Let's try with our other factor. So let's try with this one, 3 minus 2i. If x equals 3 minus 2i, what does it look like when we set the whole equation equal to 0?
X minus 3 plus 2i.
All right, so let's move that 3. We have a negative 2i, and so we're going to add that. So we get x minus 3 plus 2i equals 0. This is going to go in as my third factor. X minus 3 plus 2i. This is a good start. All right, this is a good start. This setup is super, super important. After this, we're just multiplying, okay? But we want to be very clever in how we multiply. I don't really like to work with i's, so I try and sort of get rid of them early on. So what I'm going to suggest is we keep our x minus 5 in the front and we multiply these two out, all right? So let's do some distribution, all right? We're going to take this x, we're going to multiply it by x, by the negative 3, by the 2i. That's going to give me x squared minus 3x plus 2xi. Then what's the next thing I'm going to distribute? The negative 3. Good. I'm take this negative 3 times the x times the negative 3 times the 2i. And I get negative 3x plus 9 minus 6i. And last but not least, I'm going to take that negative 2 and distribute it everywhere. Negative 2i. So I get negative 2xi plus 6i minus 4i squared. Definitely a situation where things look a lot worse before they look better. All right. Is there anything that I can cancel out here or combine with a different term? Okay, so I see this negative 6i and a positive 6i. Those are going to go to 0. Good. I see someone else has said that the negative 3x and a negative 3x, those are going to combine to make a negative 6x. That's good. Anything else go away or combine? 2xi, negative 2xi. That's good. A lot of stuff is going away. And I would argue that there's another pair of like terms, but it's like a secret pair. Oh, yeah. You see this last term here, negative 4i squared? What's another way of saying I squared? I squared equals negative 1. Good. So really, negative 4i squared is the same as negative 4 times negative 1, which equals 4. Negative 4i squared equals negative 4 times negative 1, which is the same as positive 4. That means that I can combine this positive 4 with this positive 9, secret like terms. All right. So what do we have after we get rid of all this stuff and combine terms? We get x squared minus 6x plus 13. All right, we are almost done here. We got to distribute one more time. We're going to distribute the x to the x squared, negative 6x and 13. and then the -5 to all three terms as well. So we get x cubed minus 6x squared plus 13x minus 5x squared plus 30x minus, let's see, 3 times 13 is 65. We go through, we combine.
Quick question.
Terms. Yeah, what's up?
Oh, wait, never mind. You got the one that I was messing with. Okay.
Okay. All right, so we got x cubed minus 11x squared plus 43x minus 65. So lots of different parts to this, but I would say the biggest piece I'm looking for is that setup. If you have the setup, that means you remembered that the imaginary zeros come in pairs. That is, they are always with their complex conjugate, even if it's not listed. The rest of this, the calculation part, I would say the most important part is at the end, you shouldn't have any i's left. If you have some i's left, something went wrong. Okay, so go back and make sure that you've distributed correctly, but it's actually a really good indicator whether you're headed in the right direction or not. Okay. All right. Let's take a look at example 5, which I think will be very similar to this. And let's talk about the setup and maybe some strategies on how we can work through this in an efficient way. Okay. So number 5, I have this polynomial. It has some real zeros, as in 2 is a real zero, 3 is a real zero, and I is an imaginary zero. What else is automatically also a zero? There we go. All right. And -I is also an imaginary zero. This is critical to making sure there are no i's at the end of your answer. Okay. If you still are getting i's at the end of your answer, it is very likely that you forgot this thing that I'm going to circle a bazillion times so we remember that we have to have the complex conjugate. Okay. It's easy to forget, but it's also easy to think about, okay, where did I go wrong? Did I remember that complex conjugate? Right? It's a good checkpoint for ourselves. All right. Talk to me about the factors. If x equals 2 is a 0, what is the corresponding factor? Good. All right. If x equals 3 is a real 0, what is the corresponding factor? Beautiful. All right. If x equals I is a 0, what is the corresponding factor? Yes, x minus I. Good. And if x equals -I is a 0, what is that corresponding factor? Yeah, x plus I, right? Because we said here x equals I, we want to make it equal to 0, we get x minus I equals 0. And over here, if we have x equals negative I, then x plus I equals 0. And so that's where those imaginary factors come from. Okay. Now let's talk some strategy. If I were to think about maybe making my own life easier, I might think, oh, let me go ahead and do the real parts first. And then separately, let me do the imaginary parts, right? So I almost turn this into like two mini problems in my head where I'm looking at the real parts and then the imaginary parts. I would get something here and I would get something else here. Okay. Let's take a moment. I trust you folks to do this one, x minus 2 times x minus 3. That you can do. Let's make sure we are doing this x minus I, x plus I correctly. Okay. So x times x, x times I, negative I times x, negative I times I. X squared plus xi minus xi minus I squared. What stays? What combines? What goes away?
The xi's go away, and then the negative I squared becomes +1.
Good, good, good. All right. So really, this becomes x squared plus 1. Okay. This is, again, a good checkpoint for myself. I don't have any more i's here. That is a good indicator that I'm headed in a direction I want to head in. Okay. All right, let's go back and do the quote unquote easier parts now, or more likely the parts that are more familiar to us. What do we get when we multiply out x squared or x minus 2 and x minus 3?
X squared minus 3x. And then you get the negative 2x plus 6.
Good. And we can clean that up to get x squared minus 5x plus 6. Yeah. And then we go ahead and we distribute out. Now, let me ask you something. Do you think it would be more efficient to distribute this like this? Or this way? I think it could really go either way. I just want us to be aware that we always have a choice. Okay. We don't always have to go from left to right, especially if we're doing multiplication. We can choose a direction that is more efficient for us. And so for me, when I think about these, it's easier for me to distribute something once and then do a second distribution than it is to distribute 3 different things. But that's a personal choice, and your choice might be different than my choice. Okay. Either way, we should get x to the 4th minus 5x cubed plus 6x squared plus x squared minus 5x plus 6. And when we clean that up, we get x to the 4th minus 5x cubed plus 7x squared minus 5x plus 6. So the takeaway from this problem, these last two problems, is sometimes we're given the zeros and we want to find out where they come from. And if we think back to sort of the part that we did right after break, we went in the opposite direction, right? We started with a polynomial and we tried to get it into its linear factorization. So what we're doing here is really looking at two sides of the same coin. Like here it is all multiplied out. Now I want you to unmultiply it. Or here it is divided up and now I want you to multiply it out. Okay. So I know we covered a lot in today's class. I think that it would be really important to engage with this content over the weekend, like more than just like, oh, okay, I did the quiz and that was really hard and I hope these questions don't come up again. But like chapter 3 is all the different parts really match up with each other. Okay, so it's a good time to sort of pause, reflect on the story that we've seen so far in chapter 3 and kind of be really grounded in that before we continue to add to it on Monday of next week. Okay. So we're going to stop the lecture right here. I'm going to go ahead and stop that recording.